In this video, we are going to see now an example of what we call a discrete base filter. So everything here is discrete, all the states are discrete, and the measurements are also discrete, and the set of functions are also obviously discrete. And you know the state and the scene is the following. We have a robot like the yellow robot that you see over there. It's equipped with a proximity sensor, and effectively the job here is to estimate the state of the door, whether the door is open or closed. Okay, so we have a binary state in this case, and as we will we will start from a situation where we have absolutely no knowledge about the state of the door, and the state of the door is discussed here, as we said in an earlier, with a belief. Is denoted here with this belief of S0. 0 is the initial state, t is equal to 0 in this case, and the state, as we said, can take two values, open or closed. Therefore, we are each of these posterior probabilities is one half. Okay, so that's basically the starting kind of point, and we will be using, if you like, the sort of a formula for the general kind of base filter that we have seen kind of earlier. Okay, so this formula is going to be applied now first, and actually this is basically what we actually wrote. So we are going to have a for loop. In this kind of for loop, we're going to have the first step over here. So let's see that how it is done. Okay. Now, before we apply this kind of equations in the base filter, we have to assume and to specify the two probabilistic models that we had, the generative models we have mentioned that we need. The first is the measurement model, and the second is the transition model. So in the measurement model, we have translated from English sentences in this kind of table to the probability distribution, to a probability distribution that you see here. So the first line is that if it's open, the agent can sense that it is indeed open with a probability 60%. So that's my conversion to the probability. If it is open, the agent can sense it as closed with a probability 40%. If it is closed, the agent will sense it as open with probability 20%. And if it is closed, the agent can sense it as such with a probability of 80%. Okay, so all of these, we have two possible states that are either open or closed, and we have two possible senses, again a binary measurement, and in this case we have four possibilities that we specify in this distribution. Now you're going to ask where are these probabilities came from, why 0.6 and not 0.7 and so on, and the answer to that is that these are basically a simple assumption in order for us to make a case and understand how the discrete base filter is implemented, and most of this kind of information will be obtained from the data sheet of a sensor vendor, and that will actually be enough for us to be able to quantify in that kind of case equivalent probability distributions based on the histograms in terms of errors and things like that they are reporting typically in those data sheets. Okay, so that's basically the measurement model. And now let's transition now to the transition model. And in the transition model, we will see now two variables which are being conditioned. And because of that, we will expect to see a much longer kind of table. So we see the transition is going from, it requires a specification of an action. So it is the earlier state, an action of open, an action of push, and a subsequent kind of state. And these are all the possibilities. I am not going to go through line by line through the table, but you can actually see how we are actually specifying this that we need to specify all these probabilities. And we have, of course, 8, a length 8 kind of table, because we have 2 to the power of 2 and times 2. 2 to the power of 2 is coming from the presence of the 2 conditioning variables, and another 2 is because of the 2 possible states of the starting state, okay, of the ending state. Okay, so we have that's basically the transition kind of model, and we will now use, we're ready now to write the base filter and apply it. So we will be applying it at discrete time instances. So we were in time instance equal to 0, where the whole process kind of start. And now we are starting with specifying what will happen at time instant t is equal to 1. So at time instant t is equal to 1, the agent takes no action and senses the door as open. Okay, so we have an A and we have a Z, and we are now on applying the first step in that base filter pseudo Python kind of code that we wrote earlier. So the first is a line is the prediction step, and here we are summing over all possible states st or st minus 1. So we are in S0, so over all possible states S0, and this will be the remaining kind of terms associated with the sum rule, the conditioning times the belief, the posterior of the state S0. Remember that the posterior of the state S0 was actually given to us, and it was 1/2 for both of the possible situations, both of S0 is equal to closed and open. So we have a binary state, so we're expecting to see in this summation 2 terms. That's the first term and that's the second term. And no surprises there if we specify the transition model as it is given for the state S0 open, and if we specify the transition model for when it is closed, then we are going to estimate a belief hat that the next state, our state, is open, which is again 0.5, and this should not be a surprise because the door will remain in terms of uncertainty. We are still not sure about the state of the door because we took no action. So no action should intuitively result in no update of the belief that we have about the state. So we're still at 1/2. Okay, so the recursion, the step 2 now comes. So the step 2 involves the measurement update. And remember that the measurement says that the door is open. Okay, so, and based on the earlier discussion, we're expecting to see some reduction in the uncertainty. So let's see if that happens. So we believe that here is the general equation about the posterior belief about the state S1. So S1 evidently will still be binary, either open or closed. And this will be the general equation, and we applied for both options of the state S1, both open and closed. And in that case, we have the normalizing factor, eta. We will leave it as such. And here we have this part is coming from the measurement model, which we'll look up from the lookup table we have specified earlier. And obviously the belief hat of where we believe we were given the action we have taken, the inaction we have taken effectively earlier. That is the one that we will plug in over here. All right. So mind you that over here we need to also write the belief hat for S1 is equal to be closed, and this is again 0.5. So that's the reason why I didn't write it over here. All right. So we are replacing the 2. So 0.6 from the lookup table times 0.5 is eta times 0.3, and the posterior for closed is eta times 0.2 times 0.5. Okay, so this there is an eta which is actually missing over here, and for these two posteriors, for these two posteriors, obviously for these two posterior probabilities, we need to specify at the end of the day a posterior probability distribution, a proper distribution, and this requires that the summation of these two should be equal to 1.0. Okay, so based on that requirement, we are summing the two, the eta times 0.1 plus eta times 0.3, and make it equal to 1.0. And from that equation, it's very easy to estimate the eta, the normalizing constant of 2.5 in this case. And based on that, we can actually go back and update the posteriors for open or closed. So we can actually see that the moment we have received a measurement that indicates that it's open, that immediately improved the certainty, or reduced the uncertainty, if you like, about the state at time is equal to 1. And this now we believe that there is more likely that the door is open. Now this is the time to pause the video. Don't look at the solution and just focus on going back to that equation that we have wrote earlier about the Bayesian kind of filter, and look at the do it yourself with your own kind of sort of way to come up with an estimate of the posterior probabilities for time is equal to 2. And if you can write down what I'm going to tell you now, that's the input for your calculation. The agent is going to push the door. That's the action that will take at time is equal to 2, and will also sense that the door is open. So for these measurements and action, go ahead and calculate the posterior probability for the door state. You need to come up with a belief of S2, and you obviously need two values because S2 is a binary. So you have to come up with that, and then come back here and check that your calculations are correct. And this, if you do that, this actually also closes the discussion about what happens in the discrete case. And the discrete case is fairly straightforward in terms of calculations. Evidently, the discrete case is the simplest possible discrete case that we can ever have, where everything is kind of binary over here. And then we have a Python notebook now that we are going to go through to understand, what is happening in a bit more general case where we have non-binary. Although if you understood this kind of section, that's kind of plenty. But more importantly, we will be dealing next with the continuous dimension. This is it's a single-dimensional continuous space for my state and the measurements. And both of these probability distributions will actually be Gaussian instead of being discrete. Let us now look at the notebook. The notebook is called the discrete base filter section. And we are going to actually see here an example where we have 3 doors in a hallway. These doors at locations 0, 1, and 8. And we would like to get an understanding about where is the location of our agent. And as we actually can see here, the notebook is actually fairly long, but I will actually focus here into the most important part, which is towards the middle, where we have this discussion about exactly the similar discussion we had just in a previous video on the robot standing in front of a door. Now here the discrete state space is not 2. The door is not open or closed, but in fact we have a state which is associated with location, and in the location space we have here 10 discrete location values from 0 to 9. And as you can see, we start with some effectively claiming that we have a uniform probability distribution of our belief in a very similar way as we started also with a uniform probability distribution in the door example. And here we have, let's say, 1/10 of that kind of a probability being in each of these 10 states. Then we are going to be calculating our posterior, assuming that we have no action with respect to the agent, and we are going to effectively however, we do have a measurement, and this measurement is shown actually also here as Z, and with the measurement is equal to 1 here indicates that the agent is in front of the door, and we are going to update with the posterior the belief that which we call belief earlier, and this is what we get. So our prior effectively is our belief hat, and effectively remained the same as we get just getting started, and then the this posterior here, the posterior plot is our belief in a similar way as we had no action, but we did have a measurement in the t is equal to 1 case in the door example. So the notebook and the robot that we have just seen are pretty analogous with respect to what they do. So here we have the update, which is the measurement update for that specific measurement. And now what we will do is we are going to take a step. We are going to move. So we are moving from left to right, starting from some kind of location. And in this location, we are starting from, it was obviously an unknown location to us, but we have here the measurement, which is actually coming in, now is also indicating that we are seeing a door. So after we moved, we are also receiving the measurement. So what happens to our belief hat and our belief? Well, the belief hat change. This is actually shown here on the left, which is called prior, and we can see that the belief has moved. So from by 1. So if you compare the posterior that we had earlier, and this posterior has become the prior in this kind of iteration. This comes as an argument into our base filter, and it sort of results into this posterior now after this movement and measurement update. Notice that this is pretty much indicating a very high possibility that we are in location 1. So there are effectively 3 doors in the system. One door is in location 0, the other door is in location 1, and the other door is in location, I believe, the location 8. So these are the 3 doors that are present. So since these 2 doors are consecutive to each other, and we got 2 measurements here and here that are indicating we're in front of the door, then there are only 2 consecutive doors in this kind of hallway. There's no ambiguity. The posterior distribution is actually indicating that this is the case, and the robot is now present in location 1 with high probability than others. Okay, so the system will actually continue and update like this. So we have here the belief hat. Given that kind of posterior, we have yet another movement. This is indicated here by the predict step, that movement to the right. So the predict step effectively, as we discussed, changed the prior. This is the belief hat. And as you can see here, it introduced also some more uncertainty into the distribution. If you compare this posterior that we started from in the previous iteration to this after the movement to the right, the distribution a bit more smeared, indicating larger uncertainty. And then a measurement arrives, indicating that we have not a door, and then for sure we are after door 1, and therefore our posterior, our measurement, in other words, agrees and reinforces the prior information, and so we are actually correcting the prior, forming the posterior, okay, with the likelihood. Okay, so effectively that's the base rule that we're applying over here. Okay, and the whole thing, the previous posterior becomes, after the measurement, after the prediction step, the prior for the measurement, for the subsequent measurement update. And we are actually proceeding as, with exactly the same way, and we are obtaining, if you like, a posterior probability distribution that actually moves together, as you can see, where with the location of the agent, of the robot. Okay, so the diagram over here is sort of the previous kind of discussion indicates exactly what is happening, kind of a bit more visually. This is really the function that implements the discrete base filter. And you can see here we are starting with a belief hat and a belief, which are empty arrays, and with an initial belief of 1/10 for each of the 10 locations. And we are enumerating with a for loop to first with a predict step to get our belief hat, and append to the list over here. And with the update step, we are considering in the update step the likelihood, which of course brings in the measurement, and the belief hat to form the update step, as we have also seen in a handwritten form of this base filter earlier. And therefore we are returning both of the priors and the posteriors, because we also would like to be able to plot them and sort of create some form of an animation. As we are moving this slider in this kind of notebook, we will be able to see how the prior and the posterior steps are being drawn. Okay, so I'm not going to go through the animations, but definitely you are able to run this notebook in your own environment or in Colab, provided of course you install all the necessary kind of packages. And we have developed a video on how to run the site itself in your own local environment, because all these packages have been pre-installed, and you are able to execute all the notebooks of this course, as well also this video. So what we will do next is that we will be looking at the continuous case now, which is a bit more exciting in the sense that it really introduces a family of Bayesian filters called Kalman filters, which they assume Gaussian distributions for both the measurements as well also the state. So we're dealing with continuous states, and this is what we will discuss next.